How are we doing tonight?
Doing pretty good, Professor. How about you?
Good, thank you. So, what I had planned for tonight is the last time we met, we had a little midterm. And so I did get the chance to grade those midterms over the weekend. And if you hadn't had a chance, please go check out the comments that I put on your midterms. And I thought that's what we should go over first thing tonight. So before we start with that, I'm sure you can see my screen. That's where we're going to start. But before we do, does anybody have any questions they'd like to ask? Okay. Alrighty, so I'm assuming you can see my screen. Somebody give me a holler if you can't.
I can see it, Professor.
Okay, thank you. All right, so let's just start with problem number 1. See the given figure for the beam. And I gave you strength of concrete. I gave you the yield strength of the rebar. And I asked 3 things. Find the nominal moment capacity. Check the minimum steel, minimum beam width, and maximum steel for this particular beam. And then find the allowable moment capacity. Okay, so this is a classic analysis type problem. Go down just a little bit so you can see there. So I called out that the beam is reinforced with 8 number 11s. The ties are number 4 ties, which you'll need to figure out what the minimum width is. And the dimensioning is such that the width of the beam is 18, the depth of the beam is 34, the distance from the top of the concrete to the center of the upper row is 28.88 inches, and the distance from center to center of the rows of steel is the 2.41 inches. So that defines the beam and basically gives you all the dimensioning that you need to find the capacity. If at any time that I'm going through this exam that you have a question or you want some clarification, just shout it out. We have plenty of time to go through this. So the area of steel is 8 times the area of a number 11 bar, which is 12.48 inches squared. Again, I just want to make sure that it is clear that you can only get the area of a rebar from the tables. And there's tables in your textbook. There are tables in the lecture. There are tables in the code book. From one of those 3 resources, find the published area of steel. You may not calculate the area of steel based on the area of a circle. That does not work and is incorrect. So please do not do that. Always, always either memorize them or get them from the tables. The next step is to calculate your effective depth of A. So A is ASFY over 0.85 F prime C B. I'm sure you noticed that I gave you an F prime C. That's an odd number, 5,500 PSI. So you have to do some of these calculations by hand. I got 8.90 inches for effective depth A. D is the distance to the top row, 28.88, plus halfway to the next row. This is 8 number 11s, so they're balanced. You have 4 number 11s on the top, 4 number 11s on the bottom. So the center of gravity of the whole group is exactly halfway. So that's 28.88 plus 2.41 over 2 is 30.09. And so the nominal moment capacity, which is Mn, is ASFY times D minus A over 2, which I got 19,195 kip inch or 1,599.6 kip feet. Are there any questions about part A?
No, Professor.
Okay, thank you. All right, so part B asks that you calculate the minimum steel, minimum beam width, and maximum steel. So the minimum steel comes from the two equations. One is 3 square root F prime C over Fy, and the other is 200 over Fy times B times D. Of the two, the greater is the 2.01 inches squared, so that controls. And 12.48 is certainly greater than 2.01, so we have no problem with minimum steel. The minimum width required, you go into your textbook, table A13, I think, or A7, I forget which one, but you go into the textbook table in the appendix, and you look at the width of 4 number 11s, and with the number 4 tie, that is 14.46 inches minimum. We have 18 inches, so no problem there. Next step is to find the maximum steel. Well, maximum steel is confirmed by finding epsilon sub t. So we have to find epsilon sub t. To find epsilon sub t, we have to find C. To find C, we need beta 1. So beta 1, you cannot look this one up in the tables because I gave you this odd number. So you have to use the equation, which is 0.85 minus 5,500 minus 4,000 over 1,000 times 0.05. And that gets you a beta 1 of 0.775. From there, we can find C is 8.9 divided by 0.775 is 11.48 inches. And then D sub T is the distance from the top of the concrete to the center of the lowest row. So in this case, D sub T is 28.88 plus 2.41 is 31.29 inches. Therefore, epsilon sub T is 0.003 times D sub T minus C over C. And I got 0.0518. Now, I'll talk about this D sub T in just a second. I'll elaborate on that in just a second. But for this solution, this is the technically correct solution. Then, because epsilon sub T is greater than 0.05, then we've made sure that we have not exceeded our maximum steel, because if we had exceeded our maximum steel, this would be less than 0.05, and it's not, so we're okay with that. Because this is greater than 0.05, phi then is equal to 0.9. And you need this phi at 0.9 to calculate your allowable moment, which is the last part of the problem. Part C is phi Mn. So nominal moment capacity is Mn, allowable moment capacity is phi Mn. Phi Mn is 1439.6. Okay, any questions about problem 1? Okay, so we covered very early on in this course, we covered the difference between D and D sub T. D is from the top of the concrete to the centroid of all the steel. D sub T is from the top of concrete to the centroid of the lowest row of steel. And don't blame me, it's ACI that made that distinction. So that when you calculate epsilon sub t, you use d sub t. Now, there are probably, in fact, I've been told definitely examples where I had 2 rows of steel and I didn't do it that way in my example. It's easy to forget that little nuance of the code. So you're conservative when you just use D instead of D sub T, you're being a little bit conservative, and it's kind of more of a practice that we do. But this answer is the technically correct answer that follows the code to the letter. So I did not deduct points for anybody who used D instead of D sub T in the epsilon sub T equation. So let me show you an alternate solution. This is the other solution to problem 1. Okay, so I have the same area of steel. I'm going to go through most of this pretty quickly. A is the same. Mn is the same. AS minimum, same answer. AS minimum. Minimum width, same answer. Beta 1. C is 11.48. But now when you get to here, okay, so if you used D instead of D sub T, again, we haven't really pressed this issue. I explored it in one lecture, but I understand that there's examples and things that I have done where I did not. When we went to double row, we didn't really hit home on this. So I didn't make a big deal out of this. If you used right here, D instead of D sub T, then okay, just being a little conservative. But what that does is it does drop this below 0.005. So if you use D here instead of D sub T, you get this epsilon sub T. If you get this epsilon sub T less than 0.005, then you have to calculate phi. Phi then becomes 0.89 because this is less than 0.005. So if I use a phi of 0.89 times my 1599.6, then I get an allowable moment capacity of 1423.6 as opposed to, oh, I covered it up, 1439.6. So the slight discrepancy, 1423, 1439. So I accepted either answer in that regard. Okay, so that was problem 1. That was the analysis problem. Any questions?
So, Professor, do you recommend using D sub T in the future, or?
The code allows that you use D sub T. And as you can see in this example, it gave you a slight bump in your capacity, but it also keeps you out of that danger zone, that 0.005 or less than 0.005. In this particular example, using D sub T got you out of that danger zone, that transitional zone, and ignoring D sub T, you had to calculate a reduced phi. So yeah, the code allows it, and I would use it anytime you can.
Okay.
Now, on the problems where we only have a single row of steel, if there's only a single row of steel, it doesn't make any difference. D sub T and D are one and the same. It's only when you have multiple rows of steel that you can take advantage of that.
So let's say we have 3 rows. Is it D sub T will always be from the top and then the centroid of the first row?
Centroid of the lowest row. Yes.
Lowest row, okay.
Well, assuming the tension's on the bottom, the lowest row. It's the centroid of the row closest to the tensile face. That I think that's
Okay.
how they word it.
Okay, that makes sense.
Okay. Any other questions? Problem 1. Okay. Problem number 2 was our pseudo analysis problem with the T-beam. So the T-beam was set up with this geometry, and I gave you what the effective flange is, 36 inches. So there was really no reason to try to calculate an effective flange when it was given as 36 inches. And concrete's 3,000, yield is 60,000, and I just defined it as 6 bars. So then I say, if the bars shown are 6 number 8s, then is this a true T-beam or a rectangular beam? Okay, and that's the question. That's the question you need to answer. Is it a true T-beam or is it a rectangular beam? So if it's 6 number 8s, then the area of steel 6 times 0.79 from the table gives you 4.74. So then little a calculates as ASFY over 0.85 F prime C be effective. And that's 3.10. So then you look at this and you say, okay, 3.10, actually, I didn't even need to do that step, did I? Eek, I don't know why I did that. Get out of my way. Okay. C and epsilon sub t actually don't need to be done here. So let me do, just so used to doing it. Put that right there. Put that right there. Okay. All you need to do is A is equal to 3.10 inches. 3.10 inches is less than 4 inches. Therefore, this is a rectangular beam. So for part A, that's what I was looking for. I was looking for 3.10 less than 4 rectangular beam. Any questions on part A? Part B, actually, this is a little different. It didn't say phi in. I said, what is the nominal capacity of this section Mn, if I remember right. This was a rough draft, so let me just block that out there. Okay. So Mn is equal to ASFY d minus A over 2. So I put in ASFY d. Now D, again, some folks had trouble with D. D is the centroid of your steel. So from the top to the top, the center of the top row is 31.5. The distance between the rows is 3 inches. So you go 31.5 plus 1.5 gives you 33 inches. 33 minus 3.10 over 2 gives you 745.4 kip feet. That's your nominal capacity. Now, if the bars shown are 6 number 10s instead of 6 number 8s, find the correct value for A. And so what you do is you say AS is 6 times the area of a number 10 bar, 7.62 inches squared. So A is ASFY over 0.85 F prime CB. That's 4.98. 4.98 is greater than 4. Therefore, let me do, that number is no longer applicable. Yeah, get out of my way. I just go up there. Okay, so therefore, once you know that this is a true T-beam, because this is greater than the flange thickness, then you abandon this number forever, and you have to calculate what the force in the flange is. The force in the flange is 0.85 F prime C, or 0.85 times 3, times the overhanging width. So 36 minus 12 is 24, times the thickness of the flange, which is 4 inches. So the total compressive force in the overhanging portions, let me draw that. So in this part and this part, the total force is 244.8. So the force that has to be in the web is the total area of steel times 60 minus the force that's in the flange, meaning that 212.4 kips has to be resisted by this area in the web. So the depth of that area is equal to the total force divided by 0.85 F prime C times the width of 12, and you get 6.94. Clearly 6.94, the right answer, 4.98, the wrong answer. And I think I deleted part D. So that was all I was looking for. So that's it. That's problem number 2. Any questions?
Just confirming, there's problem 2 sets, right?
Yes. So
Okay.
yours may not look exactly like.
Okay. Yeah.
Okay. Okay, then we go to problem 3. My eraser. There we go. Okay, so problem 3 was the design problem, where I gave you strength of concrete 4,000. I made the strength of the steel 80,000, and the span of the beam is 32 feet. All the dimensioning of the beam is given to you. So it's 34 inches deep, meaning the steel is 2.5 inches up. So D then becomes 31.5, and the width of the beam is 24. The loading has been given, 1.4 for the dead, 2.5 for the live. I made it clear that the dead load already includes the self-weighted beam. And the problem statement is find area of steel required for the given loading. And I was specific about which loading case you should use. Choose a rebar pattern and specifically use number 9s and show that the capacity is greater than the demand. And again, I think I changed this so that I did not ask for minimum steel, maximum steel, and beam width. I took those off. Okay, so to solve this, first thing we need to do is generate our loading. So the distributed load is a factored version of the service load. So I use 1.2 times the dead load's 1.4 plus 1.6 times a live load of 2.5. That gives me 5.68. And this number is kips per lineal foot. This is a distributed load. Then you have to take that factored distributed load and calculate a factored moment. Factored moment for a simply supported beam with a uniform load is WL squared over 8. So the moment is WL squared over 8, 727.0 kip feet. If by any chance you did not remember that equation, you could simply use your principles of statics, find your reactions, find your maximum moment almost as quickly. It's a pretty simple case. So this is the design moment I was looking for, 727.0 kip feet. From that, you have to find your reinforcement index, Rn. So Rn is mu over 0.9 BD squared. And the 12 is in there to convert from kip feet to kip inch. And that comes out to be 0.407 KSI or 407 PSI. And then you go to your textbook and you start looking through your tables to find out what rho is when you have an Rn of 407 PSI. What did you find when you went through your tables?
Nothing.
That's right, you found nothing. Why did you find nothing?
The
FY is
FYFC, yeah.
yeah, it's 80,000. The chart only goes to 60,000, I believe.
Exactly right. Exactly right. And that's exactly what I was looking for. I was looking for the recognition that the tables only go to 60. That's why I made this 80. I made this 80 so that you were basically forced to use this equation that I gave you, which is also in the textbook. So because this is 80, you cannot use the tables. You have to calculate what rho is based on this equation. So this equation, if you remember, is 0.85 f prime c fy 1 minus square root 1 minus 2 times Rn over 0.85 f prime c. And one of the keys in here is you got to make sure you have your units right. If you're using KSI, then your f prime c has to be in KSI. And if you're using PSI, then this would be 4,000. Okay, so that's how you get to a required rho of 00544. With that rho, you can find AS required. AS required is the 00544 times 24 times 31 and a half, B and D, to get to an area steel of 4.11. Because the problem stated use number 9s, that kind of limits your choice. And so I have to use 5 number 9s to cover 4.11 inches squared. So with 5 number 9s, I have to always, always, always check my capacity. I have to do my phi mn is greater than mu check. This is a singly reinforced rectangular beam, so I can just use my 0.9. And the way I wrote this for your version, I said you can assume 0.9. You didn't have to calculate it. So 0.9 ASFY D minus ASFY over 1.7 F prime C B. That gives you 10,458 kip inch or 871.5 kip feet, greater than 727, so we're okay. Okay, that was question number 3. Any questions on problem number 3? Anybody at all? Okay, so the last problem was problem number 4, and you had 4 fill in the blanks. Each one of them was worth 2 points. I did give, in some cases, somebody got really close. I gave them a point here. In some cases, they got, this is actually 2 values I'm looking for, and they may get one but not the other, so may get a point here. Part A, why is too much steel dangerous? Keywords that I was looking for here were basically things to the effect that too much steel means that the steel will not yield when the concrete crushes. That's the key, that the steel doesn't yield when the concrete crushes. And because the steel won't yield before the concrete crushes, then you have a situation where you have no warning, no prominent cracking, no big deflections, no signs of obvious distress so that you can vacate the building before there's a problem. Okay, so that's what I was looking for. A lot of you kind of got on the no warning, no cracking, but the other part of it was that the steel doesn't yield when the concrete crushes. That was part of the key to that one. Part B, absolute lowest value of epsilon t allowed by code, lowest value allowed before penalty. Well, those are 2 black and white answers. It's 004 and 005. What is the maximum strain in the concrete before it crushes? According to the code, 003. What is the named variable that defines that relationship between A and C? That variable is beta 1. So that's what we were looking for. Okay, so that's the midterm. Any questions?
Wait, can you repeat letter B?
Letter B,
Yeah.
0.004, 0.005,
0.004 is the lowest.
allowed by code.
Oh, I thought it was 0.003.
That's the answer to part C. 0.003 is the maximum strain in the concrete, but epsilon sub t is the strain in the steel. So the lowest allowed by code in the steel is 0.004.
Oh.
But remember, between 0.004 and 0.005, you have a pretty strict penalty that you have to calculate. And so there's a reduction of phi. You have to calculate phi between 0.004 and 0.005. If epsilon sub t is greater than 0.005, there's no penalty, phi is equal to 0.9. If epsilon t is lower than 0.004, the beam doesn't work. You can't do it. It doesn't matter what phi is, you're not allowed to do it. You have to redesign the beam.
Okay.
All right, but that's a good question. Okay, so the average for this midterm was 37.71. That was the class average. And the standard deviation was about 9.3. So what I generally say is, if you are around the average, then you're doing pretty good, not too bad. And I know that a 37 out of 50 correlates to about a 74, but it's not that bad. I mean, it's not an A, but around a 37 is C plus B minus ish, somewhere in that realm. If you have scored the average plus the standard deviation, then you're doing very well. Nothing to worry about on this test. If you scored the average minus the standard deviation, so somewhere around 28, 29 or lower, you really need to pick it up for the final. Obviously, I'm not going to name names or anything like that, but there are individuals that scored lower than 28. And if you're in that group, you need to pick it up. I would say you need to start coming to office hour if there's things that you need help with the concepts. I would say if you haven't been, you really, really need to start studying the textbook and reading those chapters. I don't know what else to say. If you're in that group, talk to me and let's see what we can do. But below 28, 29 or so, if you don't significantly raise that average up for the final, I mean, really raise that up for the final, your grade's in jeopardy. And I think we can leave it at that, unless there's any specific questions. Okay, so I got the standard end question. What was the highest grade? There was one perfect grade, 150 out of 50. Any other questions? Okay. Then let's jump into our lecture for tonight. Okay, so tonight is our introduction to column designs. So we've started with, what did we start with? Some section properties, crack moment of inertia, things like that. And then we went to strength design of beams and flexure. Then we went to, and we covered some one-way slabs. Then we went to shear design. Then we went to serviceability, cracking and deflections. And now we're going to talk about column designs. And column designs are kind of interesting because half of it is going to be about the mechanics of column design. And the other half of it's going to be a lot of what the code says about column designs. There's a lot of somewhat rigorous detailing requirements that the code has for detailing and how you tie the shear ties, how you confine the column, all kinds of stuff. So we're going to start with the mechanics and we're going to kind of progress to some of the detailing requirements. A reinforced concrete is any concrete member that supports an axial load per ACI 318 section 9331 greater than 10% of the strength of concrete F prime C times the gross area of the concrete column. So it doesn't matter if the column is straight up and down or at some kind of incline or even horizontal. Does not matter. The code does not care the orientation of the concrete member. What is the only thing that matters is how much compressive load you have on that member. So if you have less than 10% of the failure or the strength of the concrete stress times area, if you have less than 10%, then you have a beam and you don't need to worry about any of this stuff. But if you have more than 10%, then you have actually a compressive loaded member that is a column. We will divide our study of columns into 3 categories. We're going to start with columns with load eccentricities low enough to consider them concentrically loaded. A concrete column with the load going right down the middle of it so there's no moments applied. That's the first category. Second category are columns with significant load eccentricity moments, but that will fail due to material limits and a short column effect. So this is a column that has an axial load and a moment, but it's too short to buckle. So it's going to fail when the materials fail. And lastly, columns with a significant load eccentricity and slenderness that the columns might buckle prior to achieving the full material strength of the column. It is estimated that roughly 90% of all braced columns and about 40% of unbraced columns are designed as short columns. I would say even in my practice, in my career, it's more than 90% of all columns are braced columns, are considered short columns. We get into buckling or slender columns on occasion, but it may be a few years between cases. A braced column is one where some other building element keeps the column from side swaying, typically shear walls or moment frames elsewhere in the building. So the lateral force resisting elements of the building are ultimately what keeps individual columns from bending out of plane. The floors then act as diaphragms to tie the brace columns to the lateral force resisting system. So kind of a classic example is our Cal Poly parking garage. If I remember right, it's been a while since I've been to Cal Poly, but I think it's a 5-story garage. Those columns in that garage would not work if they weren't braced at every floor. They'd be too tall and slender. But they are braced at every floor because the concrete floors are poured right up against the columns. And if that column were to try to buckle out of plane, the slabs won't let it. If a column is relying on its own stiffness to prevent side sway, such as a column that is part of a moment frame, then that column is considered unbraced. So that's like the most common thing. Again, if you think of our parking garage, the smaller columns that are throughout the garage are just gravity supporting columns. They have no effect to the lateral force resisting system. And those are braced columns. They're braced by the concrete floors and they're braced by the moment frames. However, the moment frames themselves, and you can spot the moment frames because the columns are much bigger and the beams are much beefier in the moment frames. And those moment frame columns then are not braced by some other element of the building because they are the lateral force resisting system. So those moment frame columns are considered to be sway columns. And so we'll talk about what that means. ACI 318, section 625, defines a column as braced if bracing elements resisting lateral movement of a story have a total stiffness of at least 12 times the gross lateral stiffness of the columns in the direction considered. It shall be permitted to consider columns within the story to be braced against side sway. So that kind of gives you a little definition of how stiff does stiff need to be to consider them to be braced. Today's lecture will focus on concentrically loaded columns where the applied axial load does not produce appreciable moments. And we're going to consider sway columns or slender columns I guess in a couple of weeks. Okay, so of how to build a column, there are three basic types of columns, three basic ways of constructing a concrete column. Two are most common. The first is by far the most common and typically the most economical, the rectangular tied column. So there she be. It's a rectangular column. It is tied with individual hoops at a spacing of S. So these ties are regularly spaced at some spacing. You have longitudinal steel, so these black dots here and these lines here. So this is a section view and this is an elevation. These are the longitudinal steel or main or longitudinal steel. When we calculate the capacity of a column, that's the area of steel that we use because that's the area of steel that is resisting something pushing down or compressing this column. But we also have ties. Ties can be hoops or cross ties. I'm showing two sets of hoops in this case, and ties or hoops will serve to resist shear, and they're also there to do this thing called confinement. They will confine the concrete in this, and we'll talk about that in a little bit. The main steel runs the height of the column, is an integral part of the flexural axial response of the column. The ties are for the shear response of the column, as well as a very important function of confining the concrete in compression. The second is a spirally confined column. These are generally round, but they can be rectangular as well with interwoven spirals. So this is what that looks like. Usually they're a round column. The column itself has an outside diameter of h. The outside to outside of the spiral is d sub c. The diameter of the spiral is d sub b. And located on the inside perimeter of the spiral is your main or longitudinal steel. So in the side view, the longitudinal steel you can see running up and down the column. And you can see that the spiral is a continuous helix of steel. There's no start and stop, really. It's just continuous. And so when you build it into a column, you provide it with a pitch of S. So S is still the spacing of your transverse reinforcement, but it's called a pitch on the spiral because of its continuousness. The spiral is a continuous helix of rebar or wire, and the spiral confinement provides a superior confining effect and is rewarded in the ACI 318 with better capacity values. Spiral columns are generally more expensive than their tied counterparts. The third type is called a composite column, which is relatively rare, but used occasionally. And when I say relatively rare, I've never seen one. Actually, I have seen them, but only in photographs, and because they were spotlighted in some of the seismic problems of the Kobe earthquake in 1995. The Kobe earthquake, the Japanese construction used these, but they terminated the steel and just let the concrete column go up above the portion where the steel was, and that caused some problems. But in US construction, I guess we use them, but I've never seen one. So that just kind of shows they're fairly rare. But what they are is a concrete column with a structural steel wide flange or H section buried in the side. And this gives it more capacity because you got a lot more steel overall with the structural steel shape kind of buried inside of a reinforced concrete column. A composite column is reinforced similar to a rectangular tied column, except that a structural shape is embedded to add to the total capacity of the column. This type of construction is addressed by ACI 318 in sections 10.2.2, 10.5.2.2, 10.6.1.2, 10.7.3.2, 10.7.3.532, 10.7.6.1.4, 22.4.2.2, and 22.4.3.1. Composite columns are otherwise beyond the scope of this class. So this is the last you'll probably ever hear of them. But they do exist. Does anybody have any questions so far? Am I going too fast on this material?
Which one is the best compared to the three ones?
Well, that depends on what you mean by best. Which one performs best or which one is economically best?
Oh, like perform best?
The spiral, hands down.
So it has more compressive strength?
Well,
Wait, compressive? Yeah.
it does a little bit, but it's the post-peak compressive strength that actually is where it excels. I'll show you some graphs and some pictures of what I mean by that. But it does have better design factors, if you will. So you can actually design it area for, given the same square inch area of concrete, the spiral concrete column is going to give you better values, design values, than an equivalent area of a rectangular column, hands down. But the rectangular columns generally, you get better value because you get more area of concrete in a rectangle than you do in a circle. So that's kind of an offset. Like a 24-inch diameter column circle is a lot less concrete than a 24-inch square concrete column. It takes up pretty much the same architectural area, but you get a lot more concrete in the 24 square. So yeah, that's kind of outweighed by that. And then the last thing is that the spiral, it's more expensive to build than the square. So I think what usually happens is architecturally, they want the round column look, and then say, okay, well, if we're already doing the round column, let's go to the spiral and try to capture some of that performance. That make sense?
Yep. Okay.
With one exception, I'll give you one good exception to that rule. What I was talking about is mostly buildings, mostly commercial buildings. There's a whole nother field of construction out there that most of you drive under every day. And if you ever paid attention to the freeway overpasses that you drive over and under and around all the time, take a look at those piers that are supporting the mass of all that concrete. And what you'll see is that mostly those piers are either circular or they're like an octagon, like a stop sign shape, which is almost a circle. Why? Why is that? The old overpass designs were rectangular. And if you want to see those, I dare you, drive to central LA and drive on the older parts of the 101 and the 5 and the 405, those overpasses. Some of those are still rectangular. And all I can say about that is if you're driving along and you feel the earth moving, do not stop over or under one of those older overpasses. That's probably the wisest thing I can give you as advice in this whole class is do not stop under those things. They're not properly confined. They were built in the 60s. The modern piers that you see on Caltrans freeway overpasses, as I mentioned, are almost always circular or octagonal, which is almost a circle. What is inside of those overpasses are spirals. Big number 6 size spirals that are 6 or 8 feet in diameter. And those do a much better job of confining the concrete and really helping those columns survive seismic activity. So that's the Caltrans has unilaterally gone to that construction. You'll never see them build another rectangular column for a freeway overpass. Okay, so hopefully that helps paint a little bit of a picture. As mentioned, spirally reinforced columns have superior confinement properties, which gives the column superior load to deformation properties. Okay, so here's a little graph that I made. The tied column is represented by the dashed line, and the spirally confined column is represented by the solid line. And what we're showing here is if the columns have the same square inch area, 200 inches squared, whatever. So the initial load capacity of both of them is the same, more or less. But what happens is as you keep deforming the column, like pushing it over to the side, as the column keeps swaying, the rectangular column hits a peak, drifts a little bit, and then blows up. The spiral column can hit its peak, drift a lot more, and then actually gets like a second wind and then can actually pick up some more load. So this is the superiority of the spiral to the rectangular column. It's not necessarily in how much load it can be designed for. It's really a measure of how much ductility, how much you can push it over before it ultimately just blows up on you. As mentioned, spirally reinforced concrete columns have superior confinement properties, gives the column superior load to deformation properties. So this is a photograph of what really happens. This image is from the 1972 San Fernando earthquake and at the Olive View Hospital, which does not exist anymore. This column was very, very poorly confined by very sparse rectangular ties. So if you can see my little wand right here, I am pointing to a tie, and there's another tie, and another tie, and one up here. There was basically no confinement on this column. The building, you can see the drift of the mullions here. The building suffered from what's known as a soft story. That's another big no-no in seismic design. But the soft story allowed the first story to drift. The rest of the building stayed more or less upright, and the whole first story drifted over something like 1.5 feet, maybe 2 feet. Hard to gauge it in this photo, but it drifted a lot. And in that drifting, this tied column with very little confinement basically disintegrated into a box of rocks. And that is the behavior of a rectangular tied column. Now, if you put a lot more ties in here, then you can get a lot closer to the performance of a spiral. But It takes a lot more steel than what's shown in this photo.
Professor,
Yes.
when a structural fail like that occurs, do you see cracking first, or what's the first indication that a structural failure like that will occur in the future?
Well, that's a very good question. Thank you for your question. In this case, it was all seismic. It was all seismic movement. So it went from pristine, beautiful building to complete disintegration in probably 15, 20 seconds. So the warning is that the building's moving like 2 feet in each direction, really, is your sign that this is going really bad. Unfortunately, these people didn't have much warning. Fortunately, they got really, really lucky on this structure and it did not collapse. Many structures were not so lucky and the first story just pancaked straight down. During the earthquake, I mean, while the earth is still moving, you got like 15, 20 seconds to dive out the door before this thing collapses. But if you actually had like a video camera recording this thing while it was happening, you would just start seeing a whole bunch of cracking on one side, a whole bunch of cracking on the other side. And every time the building bounced from side to side, the cracking would be on one side, then the other, then the side, then that side. Pretty soon the cracking gets so severe that big chunks of concrete just fly off. It's called the cover concrete, will spall off into this big pile down here. And then as it just keeps going back and forth, it just basically disintegrates.
Okay.
Did that answer your question?
Yeah, I thought there would be like like some type of visual cue, but I guess not on this particular case.
Not for seismic. Now, if you're having a problem with a column design that is under just gravity load, that's completely different. And there are signs that you could look for distress in the column just under gravity load. That would be spalling of concrete, cracking of concrete. And perhaps what you might see is the spalling and the cracking so severe that the rebar inside of the column, you can actually see it starting to buckle on you. Those would be signs that under a gravity condition, and that would be something that you could see for weeks and months and years before it might actually get to the point where it actually collapses. That would be something different. But for lateral load, like a hurricane or an earthquake, it goes from pristine to destroyed in a matter of seconds.
Okay.
Okay, so this image, the takeaway from this image is rectangular column with very little confinement is bad. Okay, now,
Professor.
yes.
I was just observing that one, and why is the tie is so like it looks like a wire. It's not a rebar per se.
It was a number 3. It was really, really small.
Okay, I thought it was a wire.
Well, it might have been. It might have been. Remember, for this thing to have blown up like this in 1972, it was probably designed in the 60s. And buildings designed in the 60s, they just didn't have the understanding and the codification of that understanding in the code. So it's no fault of the engineer who designed this that they just didn't know any better, nor did the code require anything better back in those days. But it's because of these images, because of this building, a lot of changes have happened since 1972. And every edition of the code since 1972 has gotten a little more restrictive. They found, oh, this is still a problem, that could be a problem. And every time we get a new edition of the code, it gets a little better. So, okay, but by contrast, what are you looking at on the screen now? This is the same building. This is the same first floor. That's the same drift, like 18 inches of drift there. But this is a spirally confined column as opposed to a rectangularly tied column. You see all these wires or ties, they're very close together. So even though this column is basically failed, it's drifted so far, it's unbelievable, but it's still holding up the building above it. Which, by the way, the concrete, it went from a round column to a square column, and look how it just failed right through there. So this column is an example of good job. That was done very well. And even though this thing went way, way beyond its design capacity, it's still holding the building up. So that's the difference between very poorly confined concrete and well-confined concrete. Here's a close-up. Here's that rectangular column above it that basically is about to be destroyed. And this is the confined core. All the cover concrete is basically gone except for a little bit right there, but all the cover concrete is basically spalled and went bye-bye. But this survived and is still holding up the building. It's really remarkable.
Professor,
Yes.
how do they fix these? Like, do they have to knock down the whole building, or how do they fix these?
This one,
Yeah.
you can't. This is a miracle it's still standing.
So then the building will have to be knocked down, or what?
The entire Olive View Hospital was demolished. Yes.
Damn.
Yeah. But remember though, with seismic design, the goal of seismic design, if you get into structural engineering, if you get into what the codes are all about, the goal of seismic design is do not let the building collapse. Give people a chance to get out and survive. It's really about letting people survive the seismic event. It has nothing to do with whether or not the building is repairable or not. Now, having said that, if I'm designing a building for, say, like a magnitude 7.9 earthquake is the best that the local faults can deliver, so I'm designing for a 7.9, then if I did my job and everybody else who wrote the code did their job, if my building sees a 7.9 earthquake, it won't collapse. It may look like this image, but it won't collapse and nobody dies. That's the goal of the code. Now, if it sees a magnitude 5 earthquake, it shouldn't look like this image. It should look a lot better than this image and it should be repairable. But basically what we're told as design engineers is that building better not fall down under the design earthquake. So yes, the Olive View Hospital was studied, photographed, and then utterly destroyed and completely rebuilt in the 70s. Okay, let's see, very few. Okay, let's stop here. Let's take a break. And let's come back at say 7. Let's come back at 6:10 and start again at 6:10. Okay, can you hear me now? Somebody? Anybody?
Yeah, I'm able to hear you, Professor.
Okay, thank you.
Uh-huh.
I hate these headphones when I pick them up. Half the time I push the button, it mutes it. Anyway, thank you. Okay, we're back. And okay, so introduction to column design, axial load capacity. Okay, so very few column designs will actually be designed with a pure axial load, no applied moments. In the real world, that doesn't ever happen. But for the examination of the column mechanics, we're going to start with that idealized situation where there's no applied moments. We just have a pure axial load case. The factored axial load demand is found by using the load factors presented in lecture 4. They're all the same load factors. Like for flexure and shear, the allowable axial capacity phi Pn must be equal or greater than the factored demand P sub U. Okay, so that's the nomenclature. It's called the allowable axial capacity phi Pn. And just like flexure, just like shear, no problem is ever complete without a check that says that phi Pn is greater than or equal to Pu. Like so. So again, no problem is ever complete without doing this check. For column capacity, ACI 318 section 22.422 specifies that P naught, that's how we pronounce that little 0 right there. So we call this P naught. P naught is the nominal strength of the column with no reduction for eccentricity as P naught is equal to 0.85 F prime C, that's the stress of the concrete, times the gross area of the concrete minus the gross area of the steel, plus the yield strength of the steel times the area of the steel, right? So said 1,000 times, but a force is equal to a stress times an area. The allowable stress in the concrete is 0.85 F prime C. The allowable stress in the steel is the yielding stress. So it's the 0.85 F prime C times the net area of concrete plus the yielding stress times the net area of steel. Where AG is the gross area of concrete, AST is the total area of steel. P naught represents the maximum load that a column can carry, where all the concrete is crushed uniformly whilst all the steel yields. So theoretically, you never can carry a load greater than this value. This value has no moments included. It has no minimum eccentricity. It has no phi factor. All these things are going to reduce our allowable capacity. But theoretically, or if you took a column and put it in a crushing machine and try to crush it, this is the load you would see. That's the maximum possible load you can get out of a column. This is an ideal case. ACI 318 section 2.2 calls P naught the nominal axial strength at 0 eccentricity. Kind of a long title, but that's what P naught is, the nominal axial strength at 0 eccentricity. Any questions so far? ACI code used to impose a minimum eccentricity so that columns were designed with a minimum moment. But now the code in table 22.421 only puts an additional factor to account for minimum eccentricity. So it's kind of like a backdoor way to ensure that you're not underestimating any accidental moments that may occur on that column. So for tied columns, Pn, this is the allowable capacity, Pn is equal to 80%, 0.80 of P naught. So here's P naught, and this is Pn. Pn is less than P naught to make up for minimum eccentricity of the load or some minimum amount of bending moment applied to that column. For a spiral column, you get 85% of P naught. And this is what I was talking about. Spiral columns get special treatment. They're the special kids. So you get more capacity by design out of a spiral column than a tied column, all other things being equal. For columns with pure axial load, the extreme strain in the steel will be compressive. So epsilon sub t is going to be less than 0. It's going to be negative. A positive epsilon t is steel in tension. We were just talking earlier about how beams, that has to be at least 004, but that's a positive 004. That's tension. Columns may have steel that's in compression, so that's negative, a negative strain. And that's okay, but because the strain in the steel is less than epsilon ty, which is a positive 00207, ACI 318.2122 and table 2122 prescribe phi as, for tied columns, 0.65, and for spiral columns, 0.75. So remember, we were just talking about how if you have a beam at 005, your phi is 0.9. And if you have a beam that's somewhere between 004 and 005, then your phi is going to be less than 0.9. It's going to be like 0.88 or 0.85, something like that. Well, for columns where the steel may not even be in tension at all, it drops all the way to 0.65 or 0.75 based on the strain. So you follow the same rules based on the strain to get what the phi is equal to. These phi factors are for compression controlled columns, which are purely axially loaded columns, always will be. When we get to columns with combined axial loaded moments in the next lecture, then we will have to evaluate the magnitude of epsilon sub t to see if the column is compression controlled in the transition region or tension controlled, which will then determine that phi factor. It's the same equation for phi, but we have to calculate what epsilon sub t is and then figure out what the phi factor is. Most of the time, though, it's just going to be, this is the minimum. And for a tied column, you don't have to use anything less than 0.65. That's the bottom rung on how low phi can go. The relative magnitudes of the axial load to moment will determine the phi epsilon sub t factor. Thus, the same column under different load cases may have different phi factors. So did you get that? You could have the same column. You could be designing a column, one column, but you have different load cases. And one load case may have a lot of axial load, but not a whole lot of moment. And so the phi factor could be 0.65. Another load case, the same column, but under a different load case, could have a very minimal axial load and a very large bending moment. So that column is actually acting more like a beam than a column, and the phi factor could be 0.9. So the phi factor is a function of the loading as much as the properties of the column itself. Okay, everybody ready for an example? We're going to find the capacity of a 24 by 24 column with 8 number 8 bars. We're going to use 6,000 PSI concrete. We're going to use 60 grade rebar. And we have a dead load of 800 kips. Again, this is just pure compression. There's no bending moment. The live load is 350 kips. And we're going to have a seismic factor, SDS factor 1.45 Gs. The column has 0 applied moment, as I said. So find the allowable axial capacity, and is this column acceptable to carry the given loading here? Is this an acceptable design? Solution. Well, first we got to find a factored axial load, P sub U. So first load case is 1.4 times the dead load. 1.4 times 800 kips is 1120 kips. Or we have 1.2 dead plus 1.6 live, and that gives me 1520 kips. Or the third case is 1.2 plus 0.2 SDS times the dead and 1 times the live, and that gives me 1542 kips. 1542 is the greatest of the three, so that one controls. So now we solve for P naught. P naught, this is the equation, 0.85 F prime C, A gross minus area steel plus Fy times area steel. Gross area of concrete is 24 times 24, 576. Area steel is 8 times the area of a number 8 bar, so 6.32 total. So P naught is 0.85 times 6 times 576 minus 6.32 plus 60 times 6.32. I get 3,285 kips. Sounds like a lot, huh? That seems like, well, yeah, that worked just fine. Well, it gets knocked down a bunch. So this is P naught. The nominal capacity Pn, since it's a tied column, how do I know it's a tied column? Well, I don't have a circular spiral in there, so it has to be a tied column. So because it's a tied column, the nominal capacity P sub n is 80% of P naught. So I multiply the 3285 times 0.8, 2628. That was a pretty good knockdown right there. But the allowable capacity is phi Pn. So phi Pn is 0.65. Why is it 0.65? Because it's a tied column again. So 0.65 times Pn, 0.65 times 2628 is 1708 kips. Is phi Pn greater than Pu? Always have to ask you that. You're never done till you do this step. So 1708 is greater than 1542. Therefore, this column is acceptable. Any questions here?
So, Professor, when you say the PD and PL isn't compressive, meaning in this diagram, the force is into the page, right?
That's right. Yep.
Okay. And then the meaning of number 8 is there's like 8 rectangular thing. Like what is this? It doesn't matter what's the spacing of it. Like the
Okay.
S.
Well, good question. Let me finish the first question first. So this is what we're talking about.
Right.
Okay, just so everybody else is clear, this would be a column. So this is a section view. This is a side view. I can even do the old drafting standard here, right? Where I go, now, why didn't it change my color? There we go. So if I make a slice here and I look straight down on it, this is what I see. And so this is a side view. It's being supported on the foundation, and you have 1,542 kips of load coming straight down the middle. That's what I mean by concentric. So it's not off to one side or the other, causing eccentricity. And there's no bending moments applied, also causing eccentricity. So this is 1,542 kips of concentric load going straight down on that column. Now to your second question, when I cut a section through here and I look down on it, I've cut through so that I can see these ties. These ties that you see here are actually kind of like orientated this way. and they're at a certain spacing, like so. They have no bearing on the capacity of the column directly. So the green ties that I showed here are really just for completeness of what this thing would look like. But these ties do not add to the capacity of the column directly at all. What does add are the green dots. The green dots are the vertical steel, the longitudinal steel that is oriented like this. And so when I make this blue cut, I've cut right through number 8 bars. 1, 2, 3, 4, 5, 6, 7, 8 number 8s. Does that explanation help?
Oh, okay. So the ties is just there for like to hold the rebars?
Mm-hmm.
Okay.
Yeah, the ties are there for shear, but we're not talking about shear yet. We don't have any shear on this column. And they're also there to keep the concrete kind of in there, and they're there to hold the longitudinal rebars from buckling. So they have very important functions, but in this calculation, you did not even need to know what size of ties these are or what spacing. It had no bearing whatsoever on calculating phi-pn. The only thing that has anything to do with phi-pn is how much concrete and how much steel is actually being cut by that section cut.
Okay, that makes sense.
Okay, good question. Anybody else? Okay. Okay, so now we got some prescriptive requirements. And the code just came up with a bunch of rules that we all have to follow so that we don't have failures like the Olive View Hospital again. So the first rule is ACI 318, section 10611. The area of steel AST shall be at least 1% of the gross area, at least 1%, but not more than 8%. If the column is part of a lateral force resisting system or part of a moment frame, then ACI 318.18.741 says that you can't be more than 6%. They knock it down a little bit because the moment frames need to they need to be more ductile than just gravity columns. If the main steel will need to be lap spliced within the column, then generally you need to keep that steel down to about 4% of the gross area. And really, this is all kind of academic because you start getting up to 2 or 3 or 4% of steel. That's a lot of steel anyway. And it's getting difficult to fit it all in there. I have done column designs where we were up to 6%, but boy, those were crazy. For design economy, less steel and more concrete should always be used when possible. For column designs, raising F prime C adds directly to the column strength. So instead of a spindly little column with a whole bunch of steel, it's usually a lot better to have an oversized, robust size concrete column with minimum steel. And it's going to be a lot more economical. Minimum number of longitudinal bars. Okay, so ACI section 10731 prescribes the minimum number of bars as follows. If you have a triangular tie, which I don't think I've ever seen, but if you had a triangular tie, you got to have 3 bars minimum. If you have a rectangular or circular tie, you have to have 4 bars minimum. And if you have a spiral, then you have to have 6 as minimum. Or if you have special moment frames enclosed by circular hoops, you have to have 6 bars as a minimum. Additionally, ACI 318, 18752, items E and F restrict the maximum spacing of longitudinal bars for columns resisting seismic forces. These provisions also apply to columns supporting gravity only in structures of seismic risk categories C through F. Okay, basically what that's saying is that there are profoundly more restrictions on columns that are part of a seismic moment frame. And there should be, because those seismic moment frames take a lot of abuse in an earthquake and they have to stay standing. If a seismic moment frame column fails, then the building comes down. So it's really important. But what the code does is if you're building a building in moderate to severe seismic risk, which is all of us down here in SoCal, then a lot of your gravity columns, they're not resisting seismic forces, but because the whole building is going to be moving around due to seismic, you have to apply a lot of those restrictive provisions to your gravity columns as well. So while this provision does not dictate that number of bars, it effectively requires more bars in buildings built in regions of seismic risk. For example, a 24 by 24 column in California, the minimum number of bars becomes 8 or 12, depending on the magnitude of the axial load. So we do 24 by 24 columns all the time. And I think I've seen the last column I'll ever do that has 4 number 11s, 1 number 11 in each corner. As a minimum, they all have 8 number 8s now. Like the example that I just did, that's the minimum, 8 number 8s. But if the load on that column is greater than a trigger point, I think it's 35% of P naught. If the load is greater than that trigger point, then even 8 bars, they're not close enough. You have to go to a 12 bar pattern. And you can use 12 number 7s, but you got to use a lot of bars. And it just makes the columns increasingly more expensive, but it also makes the columns more ductile. ACI 18752 will be discussed in more detail below. Tie requirements. All right, so minimum size, ACI 318 25722. The minimum size of ties is predicated by the size of the longitudinal steel. If you have number 10 or smaller, then you can use number 3s as ties. If you have a number 11 or larger as longitudinal steel, then, or for bundled steel, you have to go to a number 4. Both of these are kind of a moot point. If you're building a column in California, it's going to be number 4s anyway. Doesn't really apply. But if you're building a concrete parking garage in Minnesota, where not only do they not worry about seismic, that they actually did a legislative movement and removed all the seismic from the code that they use. So if you're building buildings in Minnesota, you can use 4 number 11s with number 3 or number 4 ties. Very minimal. Maximum spacing. So the tie spacing is prescribed by ACI 2572 in accordance to A and B, where the clear spacing of your ties has to be at least 4/3 of the diameter of your aggregates. This doesn't ever apply. Or the center to center spacing shall not exceed the least of 16 times the bar diameter of the longitudinal bar or 48 times the diameter of the tie bar and the smallest dimension of the member. So 48 times the diameter of a number 4 tie is 24 inches. You can go to Minnesota and watch them build columns with number 4s at 24 inches on center. Not here. We don't even bother trying to go more than 6 inches on center, building a column in seismic country. So Minnesota, 24 inches. California, 6 inches maximum, probably 4 inches in the the more heavily confined regions. Night and day. The maximum spacing of ACI 318.25.7.2, item B, really only applies outside of seismic regions of moderate to high risk. Within regions of moderate to high risk, ACI 318 section 18.7, that's the seismic chapter for moment frame columns, and ACI 318 18.14 for gravity frame columns will greatly, underlined, greatly reduce the maximum allowed spacing for transverse reinforcement. This will be discussed in more detail below. Okay, tie configurations. So here's a number of different configurations that you can use for tying your concrete columns. So you can have, this is what I was talking about. This is a 4-bar pattern that you just don't see in California anymore. This is an 8-bar pattern that's becoming pretty common. And you may even have to go to a 12-bar pattern to get the spacing to work. And so ACI 25.723 specifies the configuration requirements for ties. Every corner and every alternate longitudinal bar shall have a lateral support provided by the corner of a tie with an included angle not more than 135 degrees. No unsupported bar shall be farther than 6 inches clear on each side from a tie with a lateral supported bar. Okay, so what does all that gibberish means? It means that a 4-bar pattern is fine because each one of these longitudinal bars is being restrained by a tie. If I go to a 6-bar pattern, I can only not have a tie in the middle here if this space is less than 6 inches. If this space is more than 6 inches, I have to provide a tie, something like this or like this, okay? So that's the general rule, is you can never have a space between bars that's more than 6 inches. And you can never have a rebar, you can't have more than one rebar ever unsupported. Every other bar may be unsupported, but we don't even bother trying to do this either in California. Really in California, what you're looking at is this or this or this or this. And you can see how this would dramatically increase the cost of your columns with so much confinement steel. Okay, so if your eyes are starting to glaze over and you're starting to drool on your desk, here's the short takeaway. Minnesota, California. Got it?
I have a question.
Please.
This might be weird, but why they don't put longitudinal rebar in the middle? Like, why is it all sides and corners?
Okay, because I guess there's a couple of practical reasons why you don't put it in the middle. And by the way, there's nothing in the code that says that you cannot put it in the middle. But here's the answer. For axial capacity, it doesn't matter where you put the bar at all. For axial capacity, you could put all the bars in the middle, you could put them all on the edge, you could put some over here, doesn't make any difference. But remember what I said, rarely, if ever, do you actually design a column that has no applied moments. So when you start applying moments to this column, you want the rebar as far from the center of the column as possible because it's acting like a beam. So it's kind of like the same thing. Why is it that all the beams we are looking at, all the rebars are either on the very bottom or the very top? And the reason is that gives you the most effective D to give you the most moment capacity. So if you put all the steel in the middle, you basically have you have minimal moment capacity. You put all the steel on the perimeter, that gives you the maximum moment capacity. But you can't put it all on just one side, because you can't control if the moments are only being applied in one direction. They can always be applied in both directions on both axes. So that's the real reason. And if you put a bunch of steel in the middle, it's very difficult to provide a confining tie situation to confine those in the middle. And the ties themselves have to have a rebar in the corner of the tie to make the tie effective. So hopefully that's a number of practical reasons why you hardly ever see steel in the middle.
Okay, so it's mainly for shear purposes. Right.
No, that's the last, no, mainly for flexural
Oh,
purposes.
flexural purposes. Okay.
Yeah.
Okay, that makes sense.
Okay. Ties can be provided as hoops or cross ties. So this is a hoop. It goes all the way around and it has these ears. Or you could have a cross tie, which is this dude right here. And because if you had a cross tie with this ear at 135 degrees on both ends, you wouldn't be able to get it into your formwork. It'd be too difficult. So the code does allow that one end can have this ear, this hook on it, and the other end has a 90-degree hook so that you can slide it in here, hook that rebar, and then place it and tie it. Or otherwise, you just couldn't place them. But when you use these guys, you have to alternate them. You can't put the 135 on one side always. Every other cross tie has the hook flip-flops from one side to the other. And ACI 2535 item E prescribes that cross ties be alternated end for end. That's what I was just saying. And that's the shape of the cross tie there. Spiral requirements. ACI 25732 gives you your minimum size for a spiral. The minimum spiral bar or wire diameter is 3/8 of an inch. So you can use a 3/8 inch wire, or you can use a number 3 rebar, as long as it's bent into a continuous spiral. Maximum spacing of a spiral is prescribed by 25731 in accordance to A and B. A, the spiral has to have a pitch of at least 1 inch or 4/3 of the aggregate size, but the spiral cannot have a pitch greater than 3 inches. So back to confinement and ties, right? The requirement for hoops outside of seismic country is 48 times the size of the bar. That could be 24 inches for a number 4 bar. But if a spiral, you can't go more than 3 inches. That helps describe why all of you hospital, the rectangular columns did so bad and the spirals did so much better. The volumetric spiral reinforcement ratio, rho sub S, defined by ACI 318.25.733, says that the volumetric ratio has to be greater than or equal to 0.45 gross area concrete over the core area of the concrete. So ACH is defined as this inner area, minus 1 times F prime C over FYT, where AG is a gross area concrete, ACH is a cross-sectional area of the column measured to the outside edges of the transverse reinforcement. FYT is the yield stress of the transverse reinforcement, which can be taken up to 100 KSI. And rho sub S is actually equal to 4 times the area of the wire or bar times the DC, the out-to-out diameter, minus the bar diameter over the spacing or pitch times DC squared. AST is cross-sectional area of the spiral wire. dB is the diameter of the spiral bar or wire. And that's all I gave you. So DC again is the out-to-out diameter of the wire, and S is the pitch or spacing of the wire. Okay, any questions so far? Similar to beams and slabs, we look to ACI 20.6.3.131 for coverage requirements. This is for concrete coverage for the protection of reinforcement. For columns exposed to earth or weather, ties need 1.5 inches cover, and your longitudinal steel needs at least 2 inches of cover. For columns not exposed to the earth or weather, ties need 1.5 inches cover still, but your longitudinal steel can be 1.5 inches cover, which to me is weird, but that's what it says. Now, special requirements for columns in seismic regions. Let's see. Take a look here. Okay, that was my concrete coverage, 85 to 36. I know that if I tried to go through the last just over 40 slides, we're really going to be flying through this, and it's not going to be very useful. This is a good break point. So why don't we stop here? If anybody has any questions, I'd be more than happy to entertain them. But let's save the rest of this presentation for Thursday. So, does anybody have any last minute questions they'd like to ask? Anybody at all? Okay, so slide 185, lecture 10. Alrighty then. Everybody have a nice evening. Don't forget your homework 5 is due tonight at midnight. Homework 6 has been posted to Blackboard. And we will see you on Thursday. Thank you, everybody.
Thank you. Have a good one.
You too.
Thank you, Professor.
Thank you.
Professor, I have just like a quick question, but I could wait till everybody leaves.
Sure, that's totally up to you.
Okay, thank you. Well, I'll just go ahead and ask.
They may have fallen asleep.
Maybe, yeah, that's okay. It's regarding exam 1. I looked at my grade and I didn't do so well, and I just wanted to kind of explain why, and I wanted to see if maybe you could offer anything like an extra homework assignment or extra credit to help out with my grade a bit.
Okay, no, I'd be more than happy to talk about it.
Yeah, I haven't really, like today we went over it and stuff. I still want to go over it on my own and see if I have any questions, but I did see like, you know, where I went wrong and stuff. But yeah, I just wanted to kind of explain, like I've been recently, I started working full time for the company. Like I'm just taking I'm taking 2 summer classes, and I just got a little overwhelmed with everything. That's why I think I, didn't perform as well as I wish I did. But yeah, I just wanted to kind of explain that, and I'm just trying to see if like you offer extra credit or anything.
Sometimes I do, but it's not a lot, and I certainly would not count on it. Sometimes I offer a little bit of extra credit on the final, just to help some folks get caught up a little bit, but it's just a little bit. You know what I mean?
Yeah.
I do not offer like makeup credit. Basically, I try to get everybody to stick with the pace and learn as you go, because really everything builds on everything else. That's why it's just so important that you get the foundational stuff.
Yeah.
And if you're having the issues with the theory or the foundational stuff, well, then the best thing you can do is admit to that and see where the issues are,
Yeah.
and then you really got to get caught up. So in terms of the grade, right, the homework's 20%, the midterm's 40%, but you still have a final that's another 40%. So there's no reason why you can't pass the class. I don't remember your grade specifically, but you may have done enough damage that you can't get an A. You might not be able to get a B. I don't know, but you can pass the class. But in order to pass the class, you really got to get those foundational concepts, because we just keep building on those. And the final is comprehensive. So if you don't really get what you didn't have for the midterm, by the time we get to the final, you're going to have the same problem.
Understood. Yeah, I know. I'm gonna review, my test. I'm gonna do like test corrections, and then I'm gonna catch up on maybe the concepts that I didn't really grasp. And I'm gonna study really hard for the final. And of course, I will be. I know everything's building up to it, so I'll do that. Yeah, I was just curious to see if there was an opportunity to kind of help my grade a little bit, but I think the best thing would be to just catch up and study more.
Definitely, definitely. I do tend to curve the classes, but that's not going to help you much either, because in this particular midterm, the class average was right about what I curved to. So there's not going to be any curving to this midterm, because basically the class achieved what the curve tries to get to. If everybody bombs the final, then you would you have some advantage of curving. But again, I wouldn't count on that either. Really what it comes down to is, once I have the midterm, once I have the final, and I'm looking at where everybody is at, basically I get to a point where, does this student understand enough of the basic concepts to pass this class? And really the system that I use for the midterm and the final and the grading and all that, it does a pretty good job of, is this student somebody that I would hire to bring into my work and start designing concrete? Or is that understanding just not there? And that's kind of the pass or fail. So back to what you need to do, you need to you need to catch up, and you need to build up. I mean, you don't have to memorize every single thing that I say in these lectures. It's a lot of information in a very short time, but you do need to understand the basics. You need to understand the fundamentals, the mechanics, how things work. Does that all help? Does that make sense?
No, that makes total sense, and I see your point, and I know what I have to do. Yeah.
Okay. Okay. But I'll be here to
Going down
help.
to the
I
final
mean,
for me.
yeah, I mean, ask questions. I mean, I'm sure it's painfully obvious, but I keep trying to draw questions out of students.
I know.
And in this Zoom virtual environment, it is so hard. Get me in a classroom in front of kids, and I can get questions out of people. I get too many questions out of people. Like, okay, I got to move on. I got to move on. But in this Zoom environment, I mean, I don't even know if the person is actually there. I mean, they could log into Zoom and go be playing video games or something. Who knows? So it's very difficult.
Yeah, it's hard, especially on professors, because there a lot of us we don't interact, and I don't myself, and I should. It's not that I'm not following along; it's just that I'm just taking notes really fast, and I'm trying to understand everything. But I can-
Understand, but yeah, just to encourage, please ask questions. If something is just like, whoa, wait a minute, what the heck? I am so lost. I know it takes a little courage, but stop, I'm lost. What are you talking about? And I totally encourage that. And then, of course, also the hour before every lecture is an office hour, and you can do the same thing.
Okay. Yeah, I know I've been trying to. It's just like I said, I recently started working for a GC company, and they're just kind of waiting on me to finish my classes. But I started working this summer, and I get off of work. I know I should probably asked to leave earlier, but I do my 8 hours, and then I'm driving